So we have Kun Lee, and he's going to talk about storage schema of time series astronomical data for artificial intelligence analysis. Kun, if you're ready, please unmute yourself. I see that you're already unmuted.
Oh, yes, I'm ready.
And you can start sharing your screen.
Hello, everyone. I'm Kun Lee from Tianjin University. And today I'm very excited to present our work on the theme of time domain ecosystem, storage schema of time series astronomical data for artificial intelligence analysis. And the content consists of 3 parts. Firstly, I will talk about the background of our work. And then next, I will give you an introduction of AstroCatR storage schema. At last, I will give you a summary, and we will talk about our future work. Okay, let's move to the first part, background. Recently, news has reported that 15 new plans confirmed in machine learning. First, AI distinguished between real and fake plans. The algorithm can upgrade 50 Kepler continuity plans to real plans, cross the threshold of planetary verification. This technique will helpfully be applied to large continuity samples from current and future missions, such as TESS. Recently, advantage in technique have provided an enormous wealth of data for time domain astronomy. However, the organization of this catalogues is inappropriate for time domain astronomy research because the time series information of each celestial object is indirect. To provide a large data sample for AI-based light cover analysis, astronomical catalogues need to be converted to time series data size, and the processing are shown in this figure. The intermediate time series data reconstruction tool has been designed and implemented called AstroCatR. Now I will give a brief introduction of it. As the figure show that AstroCatR consists of ETL processing, TS matching, and time series data storage and retrieval. The astronomical catalogues are transformed into sky room fields, and the load is balanced through the partition function. TS matching is a special design for time series data regression based on cross-match. The matching calculation is performed to generate time series data size by the overlapped indexing method and in-memory reference table. Currently, there are a variety of standards for most data size in the applications of AI techniques in light cover analysis. While images and spectra are stable and standardized products, the field related to time series is still not fully developed. A recommendation unified light cover release standard needs to be proposed for analysis of time series data based on the AI techniques. We focus on the challenges in time series metadata structure, storage schemas, strategy, and formats of exposition. Generally, time series data exposition formats needs to support CSV, feeds, and view table. We will try to make it compatible with the IVOA time series curved data models. We propose a storage schema named AstroCatR, which is a special design for storing time series data, and it conducive to time series data retrieval, demands of provenance linkage, and light cover analysis. Next, I will give you an introduction of AstroCatR. We will start it by describing the characteristics of astronomical time series data in 3 domains: writing, querying, and storage. The basic requirements for time series data storage and management include support for high occurrences writing, high throughput writing, and massive data storage, aggregate query, and distributed expansion. Additionally, the characteristics of different machine learning algorithms and deep learning models are taken into account to meet the needs of time domain astronomy data manner as much as possible. This figure shows the overall architecture of TSCAT. The common information for the same celestial objects need to be stored only once at the beginning, followed by time series tuples. This figure shows a sample of celestial objects in TSCAT storage schema. The head information includes zoom ID, RADC, HTM ID, helix ID, matched ID, and flag. And the time series tuples are currently divided into 2 groups. One for AI technique analysis, the other group is used for tracking sub-images. To make the best use of storage space, the time series tuples used in light cover analysis only record observational times and magnitude information, specifically date of observation, magnitude, and magnitude error. The tuple used for tracking sub-images records provenance information such as provenance, X and Y. We focus on the definition of metadata and topics for time series data, such as light cover analysis and tracking sub-images for every individual point of a light cover. This table shows lists the metadata and explanation for time series data. The divided and hierarchical storage are designed to support the light cover retrieval and analysis. In the divide storage schema, the data of the same celestial is changed from being stored in different area to centralized storage in the same area and divide according to its observational time. And there are 3 levels there are 3 main levels of hierarchical storage, namely memory table, transient table, and persistent table. This figure shows the data flow of light cover analysis. Start with raw images. Catalogues are extracted according to the celebration and processing. And then time series data are reconstructed through AstroCatR and exported through TSCAT storage schema. Light cover analysis based on data miner can take advantages of the convenience of databases or directly used in the time series data size generated by TSCAT. The provenance information attached to the TSCAT can access the sub-image for real images. At last, I will give you a summary and talk about our future work. We summarize the requirements and challenges of time series storage schema for light cover analysis in time domain astronomy. We made a preliminary design TSCAT storage schema. For future work, we will address storage and access of time series data while improving the availability and the scalability of TSCAT. Furthermore, the framework based on AI techniques will be designed and implemented for light cover analysis. We will try our best to establish the effective channels in the provenance of astronomical data and light cover analysis in time domain ecosystem. Thank you.
Fantastic talk. Thank you so much. We have a couple of questions and we have time probably for one or two more. So the first question is, do you plan to use the VO provenance data model?
We will, yes, we will use try our best to make it compatible with the VO provenance data model.
Excellent. Thank you very much. Another question, can this schema be extended to images and not just time series?
Maybe currently it's just for catalogues, and we will consider the image in the future, maybe.
Fantastic. Another question. Can you tell us a little bit about the data volumes and the data rates?
The data volume, we just do some experiments using the AST3 real astronomy data. It's about 300 GB, and it will be large in the future, maybe.
Excellent. Thank you very much for your answers. Any other question? Otherwise, we can also start. Oh yes, there is. Well, Francois is just commenting that the 2017 IVOA note was very preliminary, and so that's a good thing to keep in mind.
Yes, I read the documentary.
Did you look at the 2020 note? Francois is asking as well.
Yes, I read the astronomy time series the documents in 2020.
Perfect. Thank you so much for this great presentation. Very interesting.